Okay, let's dive into this. We're going to talk about software quality. And I mean really talk about it. We're going to pull back the curtain and look at the invisible architecture that makes some software just feel right, while other software is a total nightmare.
I mean, you've all been there, right? You use one app, it's smooth, it's reliable, it just works. Then you open another one, and it feels like it's held together with tape. It crashes if you look at it wrong. The secret isn't just about squashing bugs, it's about something much deeper. It's about design choices made way before anyone wrote a single line of code.
So to really get to the bottom of this, we have to look past the obvious thing, what the software actually does. We need to get into the how it handles stress, how it changes over time. That's where the real story is.
Usually, when we ask if software works, what we're really asking about is its functionality. Can it send the email? Does it play the video? Does it do the thing it says on the box? And yeah, that's the absolute bare minimum. That's table stakes. But it's not even close to the whole picture.
Think about it like you're building a house. Functionality is just making sure the lights turn on when you flick the switch and water comes out of the faucet. Great. But what about the stuff you can't see? Is the foundation strong enough to handle an earthquake? Is the wiring safe? Can you add a second story later without the whole thing coming crashing down? Those are the quality attributes. And they're the difference between a rickety shack and a skyscraper that'll stand for 100 years. So how do we talk about these invisible but super important qualities in a way that's actually useful? It can't just be vague feelings like the system should be fast. Well, software architects actually have a special language for this, a framework for turning those feelings into hard, measurable goals. And that tool, that secret weapon, is called the quality attribute scenario. It sounds fancy, but it's a brilliantly simple idea for describing, testing, and designing for all those crucial ilities. Availability, modifiability, performance, security, the whole shebang.
Now, I know what you're thinking. This looks pretty basic, right? Just a few boxes and arrows. But trust me, this simple blueprint is incredibly powerful. It forces us to get super specific by breaking down any quality requirement into 6 key parts. Let's run through them.
First up, the source of stimulus. This is just the who or the what that kicks things off. It could be a person clicking a button, another computer system flooding us with data, or maybe even just a timer inside the system itself.
Next is the stimulus. This is the event itself. It's the what. A user trying to log in, a sudden, massive spike in traffic, a hard drive failing unexpectedly, or maybe even a hacker trying to break in. It's the thing the system has to deal with.
The artifact is the where. Which part of our system is actually getting hit by this stimulus? Is it just the processor? The database? The entire network? You have to know where the impact is, and being specific here is absolutely crucial.
Then we have the environment. Think of this as the when or under what conditions. Is the system just cruising along under normal operations, or is it already overloaded and struggling to keep up? The context here changes everything. The response is what we want the system to do. Not what it might accidentally do, but what it should do by design. We want it to log the error, process the payment, and firmly block the attacker. This defines the correct action. And finally, we get to the most important piece of the puzzle, the response measure. This is what makes it all real. It's the number. How fast? Within 100 milliseconds. How reliable? With 99.9999% uptime. See, without a number, you don't have a requirement. You just have a wish. Okay. That's the theory. It's a little abstract, I know. So let's make it concrete. Let's see how this whole framework comes to life with a couple of real-world examples that architects wrestle with every single day.
Check this out. On the left is our template, and on the right, we filled it in for availability, which is all about keeping the system from crashing. So a fault happens, maybe a server just dies. The system needs to log it, tell someone, and this is the key, it has to keep on working. And the measure? The system is unavailable for no more than 2 seconds. See? This isn't just hoping the system stays up, it's engineering it so it's almost impossible for it to go down.
Or how about this one, for modifiability? This is all about how easy it is to change the system later. Here, a developer needs to change the user interface. The desired response is that the change gets made, tested, and deployed with no weird side effects. And the measure? It has to be done in less than 3 work hours. Boom. Just like that, a vague desire to make it easy to update becomes a hard, testable engineering goal. Okay, so defining these scenarios is the what we want to achieve. But that leads to the million-dollar question. What about the how? How do architects actually build a system that can pull this stuff off?
Well, they don't just wing it. They use a whole toolkit of proven design decisions.
And these decisions are called tactics. Think of them like the individual plays in an architect's playbook. If your scenario demands high availability, a classic tactic is redundancy, making sure if one server fails, a backup is ready to take over instantly. If the scenario is the problem, tactics are the building blocks for the solution.
Let's go back to our old friend, availability. This map here is basically a cheat sheet of tactics. You've got moves to detect faults before they become a disaster, ways to recover from them when they happen, and even strategies to prevent them from happening in the first place. A good architect knows how to pick and choose from this playbook to meet their specific goals.
So, let's just walk through a little story here. An architect might use a heartbeat tactic, where systems are constantly pinging each other, asking, "You still there? You good?" If the heartbeat stops, bam, a fault is detected. Instantly, an active redundancy tactic kicks in, and traffic switches over to a live backup. And to make sure no data gets messed up during that switch, they use transactions. It's a beautiful flow. Detect, recover, prevent. And now this is the part where it all comes together. Because these technical decisions, these tactics, they aren't just happening in some engineering vacuum. They are directly tied to the goals and the budget of the business itself. I mean, just look at this. You can draw a straight line. The business needs the system to last for a decade? Okay, that's a business goal. It translates into a technical need for modifiability. So the architect picks tactics like hide information to make future changes cheaper. The business needs to earn user trust? That demands availability, which leads the architect to implement active redundancy. Every choice has a reason, and that reason almost always traces back to a business goal. So here's the bottom line. The one thing to take away from all of this is that architectural choices are business choices. Deciding to spend the extra time and money to make a system more reliable or easier to change isn't a technical detail. It's a fundamental business decision with massive technical consequences. Quality isn't free. It has to be designed and built in from day one. So the next time you're using an app and it's slow, or it crashes, or it's a pain to use, don't just get frustrated. Step back and think like an architect. Ask yourself, what quality attribute scenario did they miss? What goal did they fail to define or fail to build for? Because now you have the framework to see the invisible structure that powers our digital world.